We often think of our best physical theories as just describing the universe. But what if one of them, maybe the most successful one ever, is actually constraining its very fabric? Let's talk about quantum electrodynamics, or QED. What if it's doing more than just describing nature with mind-boggling precision? What if it's also setting the rules for the deeper geometry hiding underneath everything? So we're diving into a really powerful idea here. I mean, quantum electrodynamics, it's just ridiculously successful, right? Its predictions are accurate to an almost unbelievable degree. But what if that's not just a coincidence? What if that incredible precision is actually a giant clue? A clue telling us that the very structure of QED is so rigid, it severely limits what any deeper theory could possibly look like. And this is where it gets kind of weird, because it leads to a paradox. For all of its power, some of QED's most fundamental pieces, I'm talking about things like the famous Dirac algebra, the math that tells electrons what to do, or even the very idea of spin, they're basically just assumed. They're plugged into the theory from the start. They work perfectly, don't get me wrong, but we've never really had a deep reason why they have to be that way. They're just postulated. So, okay, let's think about it this way. If QED is like a shadow cast by some deeper, more fundamental reality, then the big question is, how much freedom does that deeper reality actually have? I mean, given how incredibly precise and rigid QED is, what kind of hidden geometry could possibly exist underneath it all? All right, so let's get into it. What kind of hidden structure is even possible? As we're about to see, the rules set by QED are so tight that this hidden geometry can't just be anything we want it to be. In fact, most of the ways we normally think about geometry, they just don't work here. Let's run through a few of the usual suspects. How about a nice, smooth, continuous space? Well, it turns out that's actually too flexible. It just doesn't have enough built-in structure to force the specific rules of QED to appear. Okay, what about the opposite? A simple, neat, box-like grid, everything at 90-degree angles. That's too rigid, but in the wrong way. It creates all these preferred directions and extra symmetries that we just don't see in the physics that QED describes so well. So by ruling these things out, we're kind of being backed into a corner, but it's a very specific corner. We're forced to a pretty powerful conclusion. Whatever this deeper structure is, it has to be discrete, made of individual bits. It has to be minimal, with no extra junk or redundant information. And this is the big one. It has to be non-orthogonal, completely free of those artificial 90-degree angles. And what's so cool about this process of elimination is that it doesn't just tell us what doesn't work. It actually points us directly at a single, really elegant geometric answer. And that answer is the regular tetrahedron. It's literally the simplest, rigid, stable shape you can make in 3 dimensions. And, as it turns out, it has exactly the properties we've been looking for. Let's just quickly break down why it's such a perfect candidate. First off, it's minimal. It's non-orthogonal, that's just how it's built. And because of its perfect symmetry, it doesn't have any built-in up, down, or sideways directions. It checks every single box on our list of constraints. Okay, and this is where it gets really, really cool. The tetrahedron's geometry isn't just about the shape. It actually gives us a specific fundamental number. See, the angle between any 2 of its vertices, as seen from the center, is always the same. And the cosine of that angle is exactly -1/3. That's not a number we picked out of a hat. It's a fundamental, baked-in property of the shape itself. It's like a structural constant for this hidden substrate. All right, so we've got a shape, a tetrahedron. Great, but how in the world does a simple geometric object connect to the super complex math of quantum physics? Well, let's follow the breadcrumbs. The whole process is basically like a mathematical translation. You start with the fixed, non-right angle relationships between the tetrahedron's edges. Then you convert those geometric facts into the language of operators, the language of quantum mechanics. And then you do a standard math trick to orthogonalize the system. You're basically just translating its weird angles into a familiar 90-degree framework. And what comes out the other side? Well, it's just amazing. Because here's the incredible result. You get the Dirac algebra. That's the very same mathematical structure that in standard QED, you just have to assume is true. But here, it just emerges naturally. It's not a postulate anymore. It's a direct, unavoidable consequence of that underlying tetrahedral geometry. But wait, there's more. It doesn't stop there. You know that other huge mystery in quantum mechanics, spin? That falls into place too. Once you have this fixed tetrahedral structure, the property we call spin 1/2 isn't some extra thing you have to bolt on. It becomes a necessary required feature of the geometry itself. So here's how that works. The structure itself has this kind of twisty two-state property. If you rotate it a full 360 degrees, that's 2 pi, it comes back to the same spot, but its phase has flipped. Its sign changes. To get it exactly back to how it started, you have to rotate it a full 720 degrees, or 4 pi. And that bizarre rotate it twice behavior, that is the exact definition of a spin 1/2 particle, like an electron. So let's just take a step back and really appreciate what's being argued here. The point isn't that QED is wrong, far from it. The claim is that QED is so incredibly right, so unbelievably precise, that it leaves almost zero wiggle room for whatever might be hiding underneath. Just think of it like a checklist. Any theory trying to be more fundamental than QED has to be discrete. It has to be minimal. It has to be non-orthogonal. And it has to naturally spit out the Dirac algebra and spin 1/2 behavior. The tetrahedron is being put forward here as the only shape that checks every single one of those boxes. And if this little tetrahedron is the fundamental building block, well, that leads to a totally radical new picture of space-time. It's not some smooth, continuous fabric anymore. Instead, it's more like a crystal, a lattice, built from these fundamental dual tetrahedral units called cells. It's like a hidden geometric scaffolding for the entire universe. And look, this isn't just some fun philosophical game. This idea actually makes specific predictions about tiny, tiny effects, things you might see in atomic spectra or isotope shifts. And that leaves us with a really tantalizing final thought. Could our most precise instruments, things like atomic clocks, eventually become so sensitive that they could actually pick up the faint whispers of this hidden tetrahedral geometry of reality itself?